Assalamu alaikum everyone. Today we have to start this chapter number 8, which is about the flow in the pipelines. We have studied some of the concepts about delta P calculation or the pressure drop calculation using the Bernoulli equation and the journal energy equation, and today we will see that if we are dealing with the pipelines, then how we can actually calculate the pressure drop in the pipelines. So let us see what we have here. So here is the introduction. Let's see what we have. Liquid or gas flows through pipes or ducts is commonly used in the heating and cooling applications and fluid distribution systems. So we can either choose the pipelines or we can use the ducts to transport the liquids from one place to another. But there are different pressure calculations for both of the pipes and the ducts, and how we can measure the pressure drops. The fluid in such applications is usually forced to flow by a fan or pump through a flow section. So usually we can use pumps or fans to transport the fluid from one place to another. If we are transporting the gases from one place to another, we can use the fan, and if we are trying to transport the liquid fluid from one place to another, we can use the pumps. We pay particular attention to friction, which is directly related to the pressure drop and head loss during flow through pipes and the ducts. So whenever some fluid flows in the pipeline, there is some pressure drop, and due to that pressure drop, some heat is generated in the pipelines. Although that heat generation and the temperature change of the fluid, it is very minimum, but we cannot ignore the fact that wherever there is a friction, there is some generation of the heat. The pressure drop is then used to determine the pumping power requirement. So it is obvious that whenever there is a pressure drop, we have to overcome that pressure drop to transport the fluid from one place to another, and then we are supposed to actually calculate what is the pumping power requirement to overcome that pressure drop. Now we can either use the pipelines to transport the fluid, and either we can use the rectangular ducts to transport the fluid from one place to another. So when do we use these circular pipelines? Because whenever we need to transport the fluids at a very high pressures, then we can use the circular pipes, and if we need to transport the fluids at relatively low pressures near to the atmospheric pressures, we can use the rectangular duct. So in most of the industries, in the process industries where we have to deal with the highly pressurized fluids, we can use the circular pipes, and in our homes and offices, we can use the rectangular ducts for the heating and the cooling purposes. Now, theoretical solutions are obtained only for a few simple cases, such as fully developed laminar flow in the circular pipes. So the theoretical equations that we use, it is based on the fully developed laminar flows for the circular pipelines, but as we know that most of the time in the industries, we have to deal with the turbulent flow. So we have to rely on the experimental results other than the theoretical results. Therefore, we must rely on experimental results and empirical relations for most fluid flow problems rather than closed form analytical solutions. And now here we have the equation for the mass flow rate. So here we have the mass flow rate with the m dot, and which is equal to density times the volumetric flow rate. And if you are provided with a velocity profile, we can replace this average velocity with UR, which represent you the velocity profile of a fluid within the pipeline. Now to estimate the average velocity, we can rearrange this equation on the right hand side of the equation, rho UR dA. We can have this one here, and we can divide this one with the density and the cross sectional area to get the value for the average velocity. For the cross sectional area, we know it is equal to pi r square. Then you can simplify this equation in this form if you are provided with the this one UR, which is the velocity profile of a fluid within the pipeline. So what is this actually velocity profile? This is the shape of the velocity profile, which is parabolic in shape for the laminar flows. Okay, so like at the edges of the pipeline, you can have the maximum friction and you can have the minimum velocity, and as the fluid moves in the pipeline, you can have this kind of shape. So what we see here, that at the center of this pipeline, you can have the maximum velocity. So there is a relationship between the maximum and the average velocity, that maximum velocity is usually the 2 times of the average velocity. Average velocity, V average, is defined as the average speed through a cross-section cross section. For fully developed laminar pipe flow, average velocity is half of the maximum velocity. So this is the relationship that you can use to estimate or develop a relationship between the average velocity and the maximum velocity. Now let us see what is the laminar and the turbulent flow. Here there is a simple experimentation of the dye that you can use to differentiate between the laminar and the turbulent flow. So if you put some dye within the pipeline and some fluid is moving within this pipeline, for the laminar flow you will see that this dye will give you a straight line. What does it mean? That all the fluid layers within this pipeline, they will be following the same path as that of the previous path, so you can have the straight line. On the other hand, if you are having some turbulent flow, having some zigzag motion in the pipeline, so when you inject some dye within this pipeline, you will not get a straight line. You will see some straight line and then it will go zigzag. So that gives you the information that you are dealing with the turbulent flow. Now in terms of definition, what we have, laminar flow is encountered when highly viscous fluids such as oils flow in small pipes or narrow passages. So most of the times, if we are dealing with the oils that have the high viscosity or the fluids with the high viscosity, we can have a laminar flow. So if the viscosity is very less, like in case of water, you can have a turbulent flow. What is a laminar flow? Smooth streamlines and highly ordered motion is called as the laminar flow. So this kind of thing you will observe in a laminar flow. What is a turbulent flow? Velocity fluctuations and highly disordered motion is called as a turbulent flow. So you can see this kind of turbulent flow within this experiment. What is a transition region? The flow fluctuates between laminar and the turbulent flow. So if the flow is fluctuating between the laminar and the turbulent flow, you can have a transition flow. Now for the example of this transition flow, you can have the straight line and then there is some zigzag motion and then there is some straight line. So you will observe both the laminar and the turbulent flow within this transition region. Now you will also see the mathematical values to differentiate between the laminar and the turbulent flow. Most flows encountered in practice are turbulent. So we have been discussing this thing since chapter number 3 and 5, that most of the problems that we deal in our daily life, we can have a turbulent flow. Now how we can differentiate between the laminar and the turbulent flow? We can rely on the Reynolds number. What is this Reynolds number? The transition from laminar to turbulent flow depends on geometry, surface roughness, flow velocity, surface temperature, and the type of fluid. So these are the 5 or 6 parameters that can change the type of flow, that can differentiate between the type of laminar and the turbulent flow. Now what is the equation for the Reynolds number? Which is very simple. It is density, velocity, diameter, and viscosity. So which is equal to Reynolds number. It is basically the ratio between the inertial forces to the viscous forces. In the inertial forces, we can have an equation rho ud, and for the viscous forces we can have a viscosity part. So this is the equation for the Reynolds number that we can use to differentiate between the laminar and the turbulent flow. Now in terms of explanation, at large Reynolds numbers, the inertial forces which are proportional to the fluid density and square of the fluid velocity are large relative to the viscous forces, and thus the viscous forces cannot prevent the random and rapid fluctuations of the fluid to be turbulent. So at the large Reynolds number, the numerator of this equation will become high and the viscosity of the fluid will be low. So overall you can have the high value for the Reynolds number. At small or moderate Reynolds numbers, the viscous charges are large enough to suppress these fluctuations and to keep the fluid laminar. So in case of the laminar flow, this term in the equation, the viscosity, it is very large. So overall value for the Reynolds number can be low. So if you are dealing with the high viscosity fluids, you can have a Reynolds number very low, that makes the fluid motion to be the laminar. Now what is a critical Reynolds number? The Reynolds number at which flow becomes turbulent, we can call that one as a critical Reynolds number. So it is the point at which the flow will turn from laminar to the turbulent. The flow of the critical Reynolds number is different for different geometries and flow conditions. Now the value for this Reynolds number, it depends on the type of medium you are using for the transport of fluid. For example, if you are using the circular pipes, the Reynolds number value is different. If you are using the flat plate, you can have the different value for the Reynolds number. So its value depend on the depend on different for different geometries and flow conditions. So we will see this one. So we were talking about the critical Reynolds number. So the critical Reynolds number is the point at which the flow will change from laminar to the turbulent flow. So the value for this critical Reynolds number, it depends on various factors as we discussed earlier. So the value for this Reynolds number, it is different for the circular pipelines. It can be different for the flat plate. So we will discuss these things one by one. Okay. Now for flow through non-circular pipelines, the Reynolds number is based on the hydraulic diameter. Now for example, if we are dealing with a circular pipelines, then the value for the Reynolds number calculation would be this equation, Reynolds number rho u d divided by mu. So if you are dealing with the circular pipelines, the diameter for the pipeline, it is quite obvious that you can use in this equation. But in case you are dealing with the non-circular pipelines like square ducts, rectangular ducts, or the open channel flows, then what should be the value for the diameter you can use for the Reynolds number calculation. Now if you are dealing with the non-circular ducts or the non-circular pipelines, then we have to calculate the value for the hydraulic diameter. What is this hydraulic diameter? It is 4 times multiplied by cross-sectional area of this duct divided by Vectrid parameter. Okay, now how you can calculate the cross-sectional area? For example, if we take this one as a square duct and we need to calculate the hydraulic diameter for this square duct, what equation we can use here? 4 multiplied by cross-sectional area divided by Vectrid parameter. So what is an area of this square duct? It is A multiplied by A square, 4A square, and divided by Vectrid parameter. So what is a Vectrid parameter? The parameter which is coming into contact with the fluid. So we can have the Vectrid parameter 4 times the A, which is the length here. So the hydraulic diameter for this square duct, it will become A. Now in case of this rectangular duct, we can have different values for the length and for the width. So how you can calculate the hydraulic diameter? In this case, 4 multiplied by cross-sectional area divided by Vectrid parameter. What is an area here? A multiplied by B, so 4AB, and divided by Vectrid parameter. So we can have 2 multiplied by 2 sides for this A and 2 sides for this B. So 2 multiplied by A plus B, and it will give you the total value 2AB divided by A plus B. So this DH can be used as a hydraulic diameter to calculate the Reynolds number for this rectangular duct. The same goes for this open channel flow. So in this kind of flow, two sides are in contact with the fluid, and the bottom side is in contact with the fluid. So for the Vectrid parameter, you can have A plus A, 2A, and this bottom side which is B. And for the area, what you can see, A multiplied by B, which can show you the cross-sectional area. So for the channel type of flows, you can calculate the hydraulic diameter this way. Now if we are actually calculating the value for the Reynolds number using the statistical values, what we have here for flow in the circular pipes, if you are dealing with the circular pipelines, so we were talking about the Reynolds number calculation for the pipeline. So if we get the value for the Reynolds number less than 2300, we can have a laminar flow in our problem. And if we get the value for the Reynolds number between 2300 to 4000, we can have the transitional flow. And if the value for the Reynolds number it is greater than 4000, we can have a turbulent flow in our problem. Now this one is a simple experimentation and how we can have a transitional flow. So in the transitional flow, what you can see here, you can have some portion for the laminar flow, then maybe you can have some portion for the turbulent flow, then again you can have laminar, and then you can have the turbulent flow. So this kind of situation you can see for the transitional flow regions. Now let us talk about the entrance region and what is meant by this entrance region. So this entrance region, it is a point from where the fluid enters into the pipeline to the point where the velocity profile becomes fully developed, and this region is called as a hydrodynamic entrance region. So if you look at this figure here, these lines here represent you the velocity profile, and as the fluid moves or moves in the pipeline, at the start you can have the flutter region, and then as the fluid moves in the pipeline, you can see that there is a development of the velocity profile. So after certain time or certain length of this pipeline, you will see a completely developed velocity profile in the form of parabolic figure. So what is the hydrodynamic entrance region? So this one is a region where the velocity profile it is developing, and after this region, once the velocity profile is completely developed, we can have the hydrodynamically fully developed region. So how we are getting this kind of flow within the pipeline? So when the fluid enters into this pipeline, due to the shear forces between the surface of this pipeline and the fluid, you can have the high value for the shear stress. But as the fluid moves into the pipeline, the value for the shear stress it decreases in the center of the pipeline, and then you can have this kind of figure, the red line here. Okay, so in the center of pipeline, you will see that there is a decrease in the shear stress and there will be an increase in the velocity. So this thing we already knew from the previous discussion, that at the center of the pipeline you can have the maximum value for the velocity and you can have the minimum value for the shear stress. Now in what we have here, a velocity boundary layer. So this is a region of a flow in which effects of the viscous shearing forces caused by fluid viscosity are felt. So this is called as the velocity boundary layer, where the fluid viscosity and the velocity within the pipeline it is changing. What is the boundary layer region? The viscous effects and the velocity changes are significant. What is this boundary region? So this one is a region in which the velocity changes are occurring and also there is a change in the viscosity. Irrotational flow region, the frictional effects are negligible and velocity remains essentially constant in the radial direction. So this is the region at the center of the pipeline where you can have the maximum value for the velocity and you can have the minimum value for the viscosity. Now if we want to calculate what is the hydrodynamic entrance region, we have to rely on certain equations. So this is called as the entry length. What is this entry length? The hydrodynamic entry length is usually the distance to be from the pipeline entrance to where the wall shear stress reaches within about 2% of the fully developed value. So what is this entry length? This is the region from where the fluid enters into the pipeline to the point where you can have the fully developed velocity profile. So in terms of equation, if you are dealing with a laminar flow, the entry length can be calculated as entry length LH divided by diameter of the pipeline, that is equal to 0.05 of the Reynolds number. And if you are dealing with the turbulent flow, you have to get the equation Reynolds entry length LH divided by D, that is equal to 1.359 Reynolds number with the having power 1 divided by 4. And in terms of the turbulent flow, this is the direct equation that entry length LH divided by D will become equal to 10 times. So what does it mean here? That if you simply multiply the diameter with 10 times with the value of 10, you can have the entry length for the turbulent region. Okay, so the pipes used in the practice are usually several times the length of the entrance region, and thus the flow through the pipes is often assumed to be the fully developed for the entire length of the pipeline. So why do we use this entry length here? Because we are interested in looking at that at what is the point in the pipeline where we can have a fully developed laminar flow. So that is why we need to calculate what is an entry length. Entry length is the region of the hydrodynamic entrance region, and then you can see here are certain equations that you can actually use to calculate at what length of the pipeline you can have the development of the velocity profile. So as we know that most of the systems or most of the fluids that we have to deal in practices, it is the turbulent flow. So what we can actually do, we can directly rely on the last equation where the entry length will become equal to 10 times of the radius. So what does it mean here? If you multiply the radius by 10 times, you would actually get a point where you can have a fully developed velocity profile within the pipeline. Okay. Now let us see what is an effect of velocity and the volumetric flow rate in the laminar flow. For example, this one is a pipeline and some fluid is moving within this pipeline. So we can actually calculate the average velocity of a fluid within the pipeline, and we can also calculate the volumetric flow rate of the fluid within this pipeline. So these are the explicit equations that you can use directly. You do not need to derive these equations. These will be directly provided to you. So average velocity, it will be equal to delta p minus rho g L sine theta d squared divided by 32 mu L. So if you know the length of the pipeline, the delta p across the pipeline, and the viscosity of a fluid, you can actually estimate what should be the average velocity of a fluid within the pipeline. Similarly, you can use this equation for the volumetric flow rate, delta p minus rho g L sine theta pi d square divided by 128 mu L. So you can directly use this explicit equation to estimate the volumetric flow rate of a fluid within the pipeline. Now these two equations you can only use when you are dealing with a simple pipeline and if there is no installation of any kind of equipment on the pipeline. Okay, so these equations can be used if you are dealing only with the pipeline having no fittings on it. Okay, for example, there is no elbow, there is no joint on the pipeline, and there is no other devices on the pipeline. Only then you can estimate the average velocity and volumetric flow rate using these two equations. Now, a laminar flow in the circular pipes, we can have this equation. For the horizontal pipeline, you can directly use this equation. This one is the more generalized equation in terms of this one theta. So if you are dealing with the horizontal pipeline, the theta value will be 0, and the equation for the horizontal pipeline, it will become delta p phi d4 128 mu L. So you will be getting this equation here again. And in terms of the inclined pipeline, you have to include this factor rho g L sine theta. Okay, now the value for this theta here, if some fluid is moving upward in the pipeline, like in this kind of situation, so you have to use the positive value for the theta, and when you are using the positive value for the sine theta, the overall volumetric flow rate, it will be reduced if the pipeline is inclined in the upward direction. Now in the downward flow, the theta value, it should be in less than 1 in terms of, like, you have to see the angle, and the value for the volumetric flow rate, it will be, what should be the value, which for the downhill flow, the volumetric flow rate, it will be having the high value for the volumetric flow rate. So you have to be careful whenever you use the value for the theta here. It should be positive in the upward direction and it should be negative in the when it is inclined downward. Okay, so this is all for this lecture for today, and next time we will start this example 8-1. So you can review this example before the class, and for reviewing this example you have to see the lecture notes and also your book, because in this example we have to deal with more number of equations to calculate the head loss and delta p. So you should be having an information about chapter number 3 and 5 already to solve this example. Okay, so let's solve this one next time, and this is all for today. Thank you.